Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I'm going to talk about the exponential distribution, and we're going to first relate this distribution with what you have seen in the previous section, which is related to gamma distribution. Now, what is a gamma distribution? Well, gamma distribution has this probability density, which is depends on alpha and beta, and here we have the function that looks like this. Okay, so this is the probability density for gamma distribution. Now if you let alpha equals to 1 and beta equals theta for this distribution given here, for this density function given here, well, then our function here will be 1, so beta is going to be theta, alpha is going to be equal to 1, gamma function 1, and here we have x 1 minus 1 e negative x over theta. So we are letting alpha equals to 1 and beta equals to theta, and this result here is equal to 1 over theta. Well, this one here, the result is equal to 1 times 1 x 0 e negative x over theta, and that can be further simplified as 1 over theta e negative x over theta, and here is the function, the simplified version of that function, and we call that an exponential density function. And you can see the values for our random variable x is going to be greater than 0, and it goes on towards infinity. Now notice that when you talk about the exponential distribution above, there's only one parameter, which is theta. The exponential distribution is used to model waiting time before the first success or waiting time in between successes. For example, how long do you need to wait before being served at a restaurant, or how long will a battery in your watch can last before it needs to be replaced. So that sort of problem can be modeled with using exponential distribution. There is another way of representing an exponential distribution, and this is quite common, which is using this different parameterization. Okay, and this has something related to a Poisson distribution. So in Poisson distribution, we have this probability distribution function. So here is the probability distribution function, which depends on lambda, and we have that one looks like this: lambda x factorial e negative lambda. So lambda here is the rate. Okay, so lambda here is the rate, and you can see that in Poisson distribution, the random variable x here represents the number of successes in a certain time interval, whereas when you talk about exponential, it represents the waiting time in between successes. So there is some sort of relationship between these two random variables. So we can say that we can use some property related to the Poisson distribution, which is we're going to apply lambda, and we're going to represent 1 over theta with lambda. So here we are going to change the parameterization here. We're going to let lambda be 1 over theta. So because of that, then we have all this. We have this probability density using lambda as the parameter. And lambda here represents the rate of success, which is the same definition that you have seen when you talk about the Poisson distribution in chapter 5. Okay. Well, when you have this probability density function, you can easily show that the expected value of x is going to be 1 over lambda, and the variance of x is 1 over lambda squared. Okay, So that's the thing. And I hope you can see that if you use this scale parameter, so this is the scale parameter, scale parameterization. If this is your probability density function, you will get that expected value of x is going to be equal to theta, and then variance of x is going to be equal to theta squared. Okay. Right. Next, in this example here, we are going to prove that the mean and variance of an exponential random variable, so this is our random variable, we're going to prove the result as described in this page. So we're going to try and prove these two results here, okay? And we're going to start off with finding expected value of x. So expected value of x is just, we're going to integrate x times with fx, and our fx is this one. So here lambda e negative lambda x dx from 0 to infinity. Lambda is a constant, you can take it out and just focus on what's the remaining terms. And I'm sure you can see that this is quite a familiar problem. You need to apply the integration by parts. So we're going to let u equals to x. We're going to consider this part first. So this one here, we're going to apply the integration by parts. Therefore, du dx is going to be equal to 1. Next, we're going to consider the next part here, which is dv is equal to e negative lambda x dx. And if you apply integration for both sides of the equation, then you will get v. V is e negative lambda x. What is the constant, or the constant right next to x is negative lambda. So that's the result. And this result also can be written in this manner if you want. So negative, so lambda e lambda x. So that is another way of representing this term. And we got to apply this formula vu v du. So this guy here is the integration by parts method. Next, what is v? Well, here we're going to focus on the integration by parts. V is this guy, which is negative e negative lambda x over lambda times with u is x. It will be evaluated from 0 to infinity, minus the next one is v. V here is negative this guy, basically this term, so this is negative e negative lambda x over lambda. What is du? Du is dx from 0 to infinity. And we can simplify that to be, okay, so that's the integration by parts. And we can simplify that to be lambda. Right here we have negative x lambda e lambda x from infinity to 0. Negative is positive. 1 over lambda can be taken out as this is a constant. So infinity is 0, e negative lambda x dx, yeah? Okay. Well, now what we can have is, if you substitute this value, if you substitute infinity into this part here, x and x, you will see that the lower part here is going to get pretty large pretty soon compared to the upper part, compared to the numerator. So therefore, when you have a situation where small value divided with a big value, the result here is going to be equal to 0. And here, if you substitute 0 into x, you will get 0 for the top part. If you substitute 0 in here, you will get lambda, the value of lambda, because e lambda 0 is going to be e0. E0 is 1, 1 times lambda. So you will have 0 over lambda, which is 0. So this part here is going to be 0 really. And what you can see is that we got this point now. So we have lambda times with 1 over lambda, and you're going to integrate this part. And notice that I can bring this lambda inside this process, okay? Because this is just a constant. Sorry, this is just a constant, so you can actually, you know, playing it around. You can take it out from the process, you can put it in the process, so it doesn't matter. Well, I'm going to put this lambda here inside the process, so it's going to look like this: 1 over lambda, infinity 0. So here we got lambda e negative lambda x dx. And I hope that you are able to recognize this part. So this part here is the probability density for exponential random variable as given by this one. So this is the probability density, and we have learned about probability density. We have learned about the characteristic of it, in which if you integrate the probability density from its lower limit and upper limit, the result here is all going to be equal to 1. Therefore, what happens next is we have the result of 1 over lambda times 1, which is equal to 1 over lambda. So that's the mean of a random variable where x here has an exponential distribution. Okay, so we are able to show that one. That's quite easy to do. Now let's move on and show that variance of x is 1 over lambda squared. Okay. Now for this one right here, we know that in order to find variance of x, this is the formula that you have to apply. And we have managed to get what's ex? Well, ex is just 1 over lambda. This is 1 over lambda. We just done that part really right here. Okay, 1 over lambda. Now we need to just continue with finding what is ex squared. So what is this value? Okay, so without further ado, we have ex squared is equal to x squared. And what is fx? Fx is just lambda e negative lambda x dx, and the limits are from 0 to infinity. And lambda is a constant. You can take it out from the process. Okay, so here we go. And I'm sure you are familiar with this integral. We have no other choice but to apply the integration by parts. So here is the integration by parts, and we're going to let u equals to x squared. So du dx is going to be equal to 2x. So this is u. Next, we are going to let dv represents this part, which is e negative lambda x dx. And if you take integral for both sides of the equation, then you will get result here v. V becomes e negative lambda x over negative lambda, which can also be written as negative lambda e lambda x. Okay, so that is u and v, and we're going to apply vu v du. So this is the formula for integration by parts. Okay, now let's move on to that. So here we've got lambda, and then the integration by parts is given by this process. V is this guy, so this is v. You can write that 1 negative lambda e lambda x times with u is x squared, and evaluated at 0 and infinity. Now minus v is this guy, so here we have negative e negative lambda x over lambda, and we have du is 2x dx. So du is 2x dx, yeah, from 0 and infinity. So that's our integration by parts. Now we need to evaluate well, this value. Again, if you substitute infinity into this part, x, and this part here, you're going to get a certain small number compared to a relatively large number at the bottom, and so the result is going to be equal to 0. And if you substitute 0 into this part, you will get 0 over negative lambda, which is going to be 0. So this part here is going to become 0, really. Next, what we have is we can simplify the rest of it. So we have lambda, negative is positive. 1 over lambda and 2, you can take it out because they are constant. So we have 2 over lambda, oops, 2 over 3, 2 over lambda, yeah. 2 over lambda, here we've got 0, infinity. And then we have x e negative lambda x dx. Okay. Next, what I'm going to do is, well, I'm just going to write down this part here, 2 lambda over lambda, infinity 0 x e negative lambda x dx. And obviously from this part, you need to do another integration by parts. That's what you need to do, but I'm too lazy to do that because we have actually done this part right here. It is the similar thing, so we can just use the result from here. So what we are looking to find, x e negative lambda x dx, has already been done right here, so I'm just going to take the result. Okay, and the result of that is this thing, this guy. So this is the result, which I'm just going to plug into this position here. Okay, so that's what I'm going to do. So I'm going to write down the results, 2 lambda over lambda, and the result here is this one. Okay, so we have 1 over lambda times 1 over lambda, 0 infinity, and we have e negative lambda x dx. So that's the result. Okay, right. Now what we can do is we can consider putting back this lambda here into the process, into this process. Okay, so that's what I'm going to do. And then here we've got lambda and lambda, you can multiply that, so you will get 2 over lambda squared, and this lambda is going to be going back inside the process. So we have lambda e negative lambda x dx, and using the same argument as what I have already, demonstrated to you guys just now when we were doing this part, we know that the result here is going to be equal to 1, because this is the probability density for an exponential distribution, and then you integrate that function from the lower limit to upper limit, so the result is going to be equal to 1. Therefore, expected value of x squared is going to be equal to 2 over lambda squared. Next, we're going to find what's the variance. So therefore, variance of x is, we're going to take this value, which is 2 over lambda squared, and we're going to minus 1 over lambda, and you square it. Okay, so it becomes 2 over lambda squared minus 1 over lambda squared. 2 minus 1 is 1, so 1 over lambda squared. And that's the result that is given right here. Okay, I think that's all for now. Thank you very much for watching, and I'll see you in the next video, and I'm going to talk about 2 more examples related to this exponential distribution. Alright, see you then.